We're moving right along in Chapter 3, and we are now at Section 3.4, and two major topics that we're going to be talking about. First of all, we're going to be looking at what your book refers to as a library of functions. You may have also heard of these in the past referred to as parent functions. You need to be able to identify them either by looking at a graph or looking at an equation. You need to become very familiar with these functions, how they look, both equation and graph form. And then we're going to look at this concept of piecewise defined functions, and that'll be the latter part of our lesson. So let's start off with these, what your book calls the library of functions. This is, as you can see, called the constant function. F of x will equal some number we're calling b, and b typically stands for an intercept. In this case, we are going to be crossing only the y-axis, because you could also turn or rewrite this so that it says y equals 4. Okay, so this is that horizontal line that crosses the y-axis. That's typically what we refer to as b, the y-intercept. And I'll get my line draw tool. You're probably familiar with this. We are just going to draw a horizontal line to where it only crosses the y-axis at one point, and in this case that's the point 0.04. Okay, and so that is one example of the constant function, where it's a horizontal line crossing a particular number on the y-axis. Okay, let's look at the identity function. Either in function notation, or maybe you've most often seen it as y equals x, means the same thing. Well, this parent function, the identity function, looks like this. Obviously it has a y-intercept of 0, which is the origin. It has a slope of 1, and so the identity function is that line. Okay, pretty easy. Moving right along. Now let's look at this parent function. You can always remember quadratics. Either the graphs of quadratics will be parabolas, either regular upright parabolas, or if there's a minus sign in front of the x squared, then that flips them over so that they open upside down. I usually spell quadratic in a weird way, so maybe it helps you remember. Think of the big gigantic U in the word quadratic, because that's the shape these always make. The word quadratic literally means squared, so maybe you think of the word squared spelled with a giant U. Whatever it takes, the quadratics will always produce these parabolas. And so here is the parent function, f of x equals x squared. It always looks like this. It has the vertex at the origin. We could input 1 and get 1. We input -1, we also get 1. If we input 2, we get 4. And that's also true for -2. There is symmetry around the y-axis. And so when you're asked to graph the parent function f of x equals x squared, it will look like this. Okay, this is one that we did not cover in Algebra 2. F of x is x cubed. Well, it also passes through the origin. Well, let's just think of some inputs. If we input 1, we get an output of 1. If we input 2, we're going to get an output of 8. 2 cubed is 8. Okay, well, let's do the opposites. If we input -1, we're going to get an output of -1. -1 to the third. And if we input -2, we're going to get an output of -8. -2 to the third is -8. So this x to the third power, it's not really an S shape, but kind of, I guess, like it. Goes through. And then it's going to go through this point and then continue to widen as the numbers for x get smaller, and it will continue to widen up here as the numbers for x, the inputs, get bigger. But that's an example of the parent function f of x equals x cubed. Okay, the square root function. F of x is the square root of x. It looks like this. We have 0, 0 as one of our points. If we just look at some inputs, easy to find the square roots. We don't want to have to plot decimals, so let's find some inputs or domain members that are easy to calculate. Obviously, I can't use negative numbers, so this function does not go, this parent function does not go to the left of the origin at any point, only to the right. So if we input 1, we get 1. Let's choose a square root number 4, output 2, 9, output 3, 2, 4, 6, 8, 9, 1, 2, 3. And that should be enough. The square root function, parent function, looks like that. Okay, so another one that you should be very familiar with. Okay, what about the cube root function? Well, it's similar. It's also going to take on this square root function shape because in a way the points are a little different, but if I input 0, cube root of 0 is 0. If I input 1, cube root of 1 is still 1. But now perfect cube numbers like 8, 2, 4, 6, 8, 2. So it's a little flatter because the square root function had 9, 3. So same basic shape, but maybe just compressed down just a little bit. And that's good enough. Now, the domain is different because we can do the cube root of negative numbers. So unlike the square root function, which did not go to the left of the origin, we could not input negative numbers. That's not true here because the cube root of negative 1 is negative 1. The cube root of negative 8 is negative 3. So this one, a little different than what we saw with the square root function. It actually does go in both directions. So it does this kind of shape. Okay, and so that's the parent cube root of x. Okay, this is called the reciprocal function. And one thing you probably notice right away is we cannot input 0. But so this particular function is never going to it's never going to cross over the x-axis. It's never going to cross over the y-axis. Let's just do some real quick inputs. If I input 1, I'm going to get 1. I'm going to try to stay away from fractions as much as I can, but let's just go ahead and do 2. That's not too bad. 2 1/2. Okay, well, what if I do the input 1/2? 1 divided by a half is the same thing as 1 times 2. So a half 2 isn't too bad. Now, if you remember from Algebra 1, this is going to be a curve that forever approaches both the x and the y-axis, but never touches. We call the x and the y-axis in this case, the x-axis would be a horizontal asymptote, the y would be a vertical asymptote. Because x cannot be 0, so that prevents us from hitting the y-axis, and this function can never be equal to 0. There's never a number that we could input for x to make the function become 0. So that's why both the x and the y are considered to be asymptotes. We will approach, but we'll never touch either axis. Well, the thing about the reciprocal function is it has 2 branches. So don't forget, if you're going to input positive numbers, you should do their opposites because this always comes in 2 what are known as branches. So just be careful here. It's tempting just maybe to forget and only do one of these, and that's like being half right. So here's the other branch down in quadrant 3. Okay, there is the reciprocal function, f of x equals 1 over x. Okay, what about the absolute value function? Well, once again, I try to get my students to remember the word absolute and then just think of the word value as a big giant V, because that's the shape these take. The parent function f of x is the absolute value of x, has its vertex at the origin, and it has a slope of both positive and negative 1. And we draw our two arrows branching out from that vertex. Okay, and there is the absolute value function, f of x equals absolute value of x. Okay, so that is the list or the family of functions, sometimes known as parent functions. Your book calls them the library of functions. So you'll do well to just be able to recognize them by looking at the function itself, or can you write down the function by looking at the graph? You should be able to do both of those before our next test coming up. Okay, now let's look at number 27, and this is going to be an introduction to this idea that we mentioned early of piecewise defined functions. Well, what that means is it's a single function. As you can tell here in number 27, I have f of x, a single function, but it's represented in two different pieces. Okay, and we're going to be able to graph these pieces in subsequent problems, but let me just walk you through what number 27 is asking for. On number 27, we are supposed to find these values, these function inputs, but notice our two pieces have domains stated after them. So in other words, for this piece, this is the domain, these are the inputs, and for this piece, we're going to use these inputs. Okay, so for example, for letter A, if I'm going to do f of 0, well, this second piece does not contain 0 as an input. It's only the numbers from 2 to 3, including 3. So I'm not inputting into this second function. I will input into the first one because the x inputs for this one include numbers from -1 to 2, which includes 0. So for letter A, I'm going to use that top function, and I'm going to input 0, and I get 0 minus 4, which is -4. Okay, let's do f of 1. Well, same idea. 1 does not fit in this domain restriction. I'm only going to have to use, or I'm only going to be able to use numbers between 2 and 3, including 3. So once again, I'm going to go up to this top function, this expression, this piece, and this input does match what's defined here. So I'm going to put 1 into that top piece, and 2 minus 4 is -2. Okay, let's take a look at letter C. Well, we have the same issue. It's close. This bottom piece is only defined for x values between 2 and 3, but not including 2. This top piece is defined for inputs that do include 2. So, once again, I'm going to input 2 into this top expression. And 4 minus 4 is 0. Okay, letter D, f of 3. Well, now 3 does not match the restriction on the domain for the top piece. It's only for numbers between 1 and 2. It does match the piece that's given in the bottom here because obviously this includes the number 3. So I'm going to input 3 into the bottom expression. And 27 minus 2 is 25. Okay, so that's the idea. When you get down to the bottom of page 241, that's the kind of thing that you're going to be working on with those problems. Okay, now we're going to work on actually graphing these piecewise defined functions, and then once we come up with the graph, we'll answer some other questions. I'm going to do this a little differently than we're still going to answer all parts A through E, but I'm going to do the graph first. I think it's easier to look at a graph and then come up from the graph with these other pieces of information that are being asked for. So we're going to go to the next slide, sketch the graph of this, and then we will come back and answer whatever parts remain. So here's how you graph one of these piecewise defined functions. Okay, and I'm going to color code so we can keep these two pieces separated. Now remember, it's really one function. We're going to graph both of these pieces on the same coordinate plane, and they together, these two separate pieces, represent this single function called f of x. Okay, so let's start with this red piece. It says f of x equals 2x, or maybe you're used to saying y equals 2x. That's just a line that has a slope of 2 and it has a y-intercept of 0. The b here is 0. Okay, so let's just start off like we're used to doing, and we're going to put a y-intercept of 0, and from there we'll count out a slope of 2 up to right 1, up to right 1. Now what I'm going to do this first time is I'm going to go ahead and graph this whole line, and then we're going to come back and take a look at the domain restriction, this part right here that says x cannot be 0. We'll see what that means for our line. Okay, so for now I'm just going to go ahead and sketch this line. Get myself a running start, and I was going to color code, so give me just a second. I'll change the color. Alright, and so now there's the line y equals 2x, just like we're used to doing probably from back in our Algebra 1 days. Okay, but this part says on this particular line that we've called 2x, f of x is 2x, it's only defined if f cannot be 0. Okay, well where is x equal to 0 on this line? Well, if you're looking along the x-axis, where x is 0, of course, is right here at the origin. So what we're going to have to do is we're going to have to draw this line, but we cannot include where x is 0 on this line. So unfortunately, with the way my tool works, I cannot erase, but if I could, I would come to where x is 0 and I would erase that part of the line. And in that little erased part, I would put a circle, because this should show y equals 2x coming along, but then when it gets to x equals 0, because x cannot be 0, we're going to jump over that point and then continue on with the line. Okay, so really, I know it shows my line going through the circle, but unfortunately, you'll just use your imagination. Technically, the line does not go through x equals 0. Okay, well let's take a look at the blue piece. It's a constant function. Another way of looking at it would be to say y equals 1. Okay, well let's just take a look at the line y equals 1. The line y equals 1 would run this way. Okay, let me just go ahead and draw that whole line, and then we'll talk about the statement that's made. Okay, so here's the line y equals 1 for x values, well, forever and ever. Okay, just bear with me for a second. Here is the line y equals 1 for x equals 2, x equals 5, x equals 10. It goes on and on and on. This is y equals 1 for every single x value there is, because this line continues going forever and ever. But what does this say? This says we only want to represent the line y equals or f of x equals 1 only if x is 0. Well, where is x 0 on this line? Well, x is 0 on the x-axis right here. It's 0 on this blue line right there. So according to this, this is the only point on this line that I should be showing. So even though I drew this, and I'm not saying you have to do this every time, I just wanted to give you an idea of how this works. We really should be getting rid of all of our line except for that one single point. Okay, so the rest of this we can get rid of. So all we have is this one, used to be a line, but we're only going to show just that one single point on the line, the point 0, 1. Okay, so we've taken care of graphing the two pieces. Now let's see if we can answer some questions. Okay, well, what is the domain of this function? Well, domain, again, remember, it's looking at the x-axis, and we're trying to put together between these two pieces. The red goes forever and ever along the x-axis, both in a negative way because it's going to continue to go left and down. It's going to continue to go right and up. So the red involves every single number on the x-axis except for 0. But the blue covers 0. Okay, it's almost like we could take this blue dot and bring it down and we would fill in this red hole. Okay, so what the red line lacked, the number that it lacked, the blue covers. And so together the domain would be represented as all real numbers. Okay, let's take a look at intercepts is the next thing we're supposed to find. Do you see any intercepts? Well, there's really only one. It's this blue dot, because the red line jumped over the origin, so we don't have an intercept on the red. We do on the blue, because that one dot is the point 0, 1 sitting on the y-axis. Okay, we've already done the graph. Now let's take a look at the range. All right, range means looking vertically what numbers along the y-axis would be used if you put the two pieces together. Well, from the origin down, we're using every number because that's the way this function is going. From the origin up, we're using every number. Okay, the blue and the red basically use that same number 1 together. The only number on the y-axis that's not being used when we put these two together is 0. Okay, so we're going to express it as the range can be basically any number such that it cannot be 0. So we're basically saying the range will involve every number except for 0. Okay, and then part E, is f continuous on its domain? Well, you probably understand what continuous means. There's no breaks in it. Well, we obviously have a break right here. Our red line jumps over the origin and then continues from there. So we're going to have to say no, it is not continuous. Continuous at x equals 0. Okay, because of the hole in the graph. And that takes care of number 29. All right, Let's try another one. And once again, I'm going to take this approach. I think it's easier to go ahead and look at the graph and then come up with all these answers from the graph. So let's go ahead and do the graph. And once again, we'll use colors to keep these pieces separated. So this one function is defined as these two different pieces. So let's just go ahead and take a look at what the line, if this were y equals negative 2x plus 3. Okay, so here's 3 on the y-axis. Now let's count a slope of negative 2, up 2, left 1. Okay, and for now, I'm going to do the same thing I did before. I'm going to go ahead and draw the whole line, just so you can see how this works. All right, so back in the good old days of Algebra 1, if you were asked to graph y equals negative 2x plus 3, it would look like that. But now let's talk about what this means. The line should only show where x is less than 1. Okay? Well, on our line, x is 1 right here. Let's put a little open circle. Okay? So x is less than 1, obviously going this direction, to the left. So technically then, according to this, I should only be showing the red line from that open circle and going upward, because this is the direction that the line will take to show values of x that are less than 1. So for that reason, I'm going to come down here and I'm going to back off the rest of this line that is on the other side, or the greater than side of 1. All right. And probably shouldn't have an arrow there, but I'm not going to bother changing my line. You get the picture. Okay, and why did I leave it as an open circle at 1? Because it did not say or equal to. All right, if it did, I would have closed the circle. Okay, so that takes care of the red piece. Now let's do the blue piece. It has a y-intercept of negative 2 and a slope of positive 3. Up 3, right 1. Up 3, right 1. Okay, and I'm going to do the same thing again, and then I'm not saying you'll have to do this every time. Once you've done this a few times, you will not have to do what I'm doing. Some people in the beginning like to just go ahead and draw the whole line and then just erase the part that they don't need. Okay, so what the blue says is let's draw this line, but let's only show it for x values that are greater than or equal to 1. Well, on the blue line, we're talking about 1 being right here. Okay, and so the line that extends beyond or to the left, down and below, where x equals 1, I need to get rid of. And once again, that should be a solid circle because it says or equal to. So it's kind of, it really does make a V shape when you put the two together. All right, so now let's answer some questions. All right, what is the domain? If you take this function in the two pieces, it's going to extend to the left, up and left forever. It's going to extend to the right forever. So once again, the domain, and you might be thinking, well, what about down here? Well, the red did not include 1, but the blue did. So you really have to think of them together. They're two separate pieces, but we're going to think of them together when we state domain and range. So the domain for letter A will be all real numbers. Okay, let's take a look at intercepts. And again, that's easy once you get the graph. We only have one intercept, and that's the y-intercept 0, 3. we did the graph already. Let's take a look at the range. For the range, we are looking vertically, and we're looking to see what numbers on the y-axis are involved as y-coordinates in this particular graph if we put the red and the blue together. Well, it looks like the bottom part of our range will be +1, and then we're going to extend upward from there. And again, it was not equal to 1 with the red, but we're going to say it is equal to 1 because of the blue. Okay, remember, you think of them together. So this range is going to be numbers that are greater than or equal to 1. Okay, and now, is the function continuous or not on its domain? Well, what started off as looking like it may not be because of this open circle, in essence, that open circle became filled. I should have filled it in a little bit better there because of the blue. The red had an open circle, the blue filled it in. So yes, this is continuous. Continuous means it'll go on forever in this case 2 different directions without any breaks. And so my answer to, is it continuous on its domain? The answer would be yes. Okay, I think we have one more of these, and so let's go ahead and do the graph first. All right, the red piece, let's graph the line y equals x plus 3. That's a y-intercept of 3 and a slope of +1. Now this time, let's see if we can just, without drawing the whole line, let's just identify this is actually going to be a segment, because we're only going to show the line for x values between -2 and +1. All right, so this is where x is -2, and this is where x is -2 on that particular line. And since it says or equal to, I'm going to leave this as a solid circle because -2 should be included as an x coordinate. Okay, and I actually have one too many over here, because on the right side I should end this little line segment for x values of less than 1. So this dot here really should be open. This is where x equals 1 on this little segment identified as x plus 3 with this domain restriction. Okay, so let's just put a little line segment here. Change color. Yeah, I guess that's going to be close enough. Okay, now let's do the blue. The blue is one of those constant functions, f of x equals 5, but only if x equals 1. Okay, so in other words, instead of drawing the whole line y equals 5, we really are only talking about one point on that line, and it's the point 1, 5. Okay, now let's take care of the green. The green says we have a y-intercept of 2, we have a slope of -1, but this green line is only going to be drawn for x values that are greater than 1. Okay, so the y-intercept actually is not going to be part of the graph, this piece. Greater than 1 means I'm going to have an open circle at 1. Okay, so we started at a y-intercept of 2. We were counting a slope of -1. That got us to this part of the domain restriction. We're showing greater than 1, and then we're just going to keep on drawing the line from there with a slope of -1. All right, and this time I'll put an arrow on it. Okay, and there is the green piece. Okay, so we got the graph, and now let's see if we can answer some questions while we're here. Let's see, what would the domain be? Well, it doesn't extend to the left of x equals -2, but it looks like it does extend to the right of that, because even though these are both open, this fills those two open circles. So it looks like going to the right of -2, every x coordinate along the x-axis will be involved. This green line is going to go forever. Alright, so the way we'll state our domain is x values such that they are greater than or equal to -2. Okay, intercepts. Well, let's see, we have a y-intercept at 0, 3, and we have an x-intercept at 2, 0. Okay, looking good so far. Alright, so let's see what else we just did the graph. Let's state the range. The range is going to include this blue point that we identified as this middle piece. So we're definitely going to have 5 as part of the range. And then from there, we start at 4 and work our way down. And if you combine the red piece together with the green piece, together we're basically talking about every number less than 4 as part of the range. Okay, this red segment kind of gets picked up by this green ray and then continues on forever. So when we put those together, we're going to say 5, and then y is less than 4. We're not going to say or equal to because it's an open circle. So we'll just come back over here to our answer page. Y such that y is equal to 5, but it's going to be also less than 4. Alright, and that is our range. Now the last thing we need to answer is it continuous on the domain? Well, the way to remember continuous is it should flow without any breaks as you move maybe from left to right. And obviously this doesn't because the red and the green are disjointed here, also the blue. All three of these are disconnected at one place, and that is where x equals 1. So we're going to say that it's discontinuous at x equals 1. Okay, and that takes care of this. That's going to be your assignment for this section, and I hope this helps you, and if you have any questions, let me know.